Well, welcome back. And today I thought I'd have a go at asking ChatGPT to simulate a very simple Wiener filter. So I give it the task, and then I thought I'd run it, of course, the code straight off and see if it worked. Wiener filters have been around since the time, not surprisingly, of Norbert Wiener back in the 1930s, although they were originally kept secret in a document. I think it was called the Yellow Peril, the original document, which was made secret during the war. Kalman, of course, superseded a lot of his work because it was a state space approach rather than based on transfer functions, which is what the Wiener filter is. But the Wiener filter made a comeback in the 1970s. Many people, including myself, started working on it, and I worked on my PhD on various aspects of it myself, and a great many colleagues, including John Barrett, who worked on it as well. There's a number of ways of finding Wiener filters, and I just assumed here that I was a little bit ignorant of how to find it and let ChatGPT find it for me. So here was my question. It's rewritten the question with ChatGPT. Write Python code to simulate a discrete time Wiener filter that estimates, I put coloured, and I spelled coloured the American way, I don't know whether, I guess it knows the difference anyway. Coloured noise signal from additive white noise. Let the coloured noise be generated by passing white noise through a second order discrete system. Plot the random signal and its estimate. So basically you pass white noise through a transfer function, a linear transfer function, second order, and this gives you the simulation of a random coloured noise signal. In engineering we call it a coloured noise signal. If you were a statistician, it would be in this particular case an autoregressive process, I think you would call it, really, basically, if you were, or a autoregressive moving average if it had zeros on it. But I've left it up to its discretion to say what the second order system is. And it generates the code after all this stuff. It gives references and so on. Down here it gives, and it uses NumPy as the basic sort of maths thing. And then the Matplot library, that's really a copy of, rewritten sort of copy of MATLAB type of library. It's not the original MATLAB, obviously. It's a sort of free version. And this thing called SciPy, which I've used before, but it turns out I didn't even know it's got this Wiener filter built into it, another library. And you can have a look at it here. So it's scipy.signal.wiener. And I didn't know about this, it just sort of used it. And to say, it's a great sort of teaching tool, ChatGPT. And it tells you how to do a Wiener filter using that particular function. This gives an example here. It doesn't actually tell you, though, how it does it. It just says that's how, to do it. So it's quite interesting to see whether it will work or not. And I gave this as my transfer function. It just generated that. So this, for those of you that don't understand the sort of MATLAB-y type representations of linear systems, that's a discrete system. It's going to be 1 over, that's the numerator, 1 minus 0.9 z to the minus 1 plus 0.2 z to the minus 2. And I changed it slightly to make it a little more sort of resonance, but that one's fine. And it used 1,000 points. I changed it to 100, a couple of hundred, so I could see what's going on. It's normalized frequency, fs equals 1. That doesn't really mean a lot. It's just a discrete time system. Of course, you could start with a real system, convert it into discrete time, and then you'd have a sampling frequency of whatever it was in your conversion, using the bilinear transform or whatever method you used. And here it passes the white noise through a low-pass filter, the filter rather, B over A. And the white noise, it's got unity variance here, which is, I don't know whether I asked that or not actually. endpoints, so it's like a vector of values. And then it adds, and again it did this itself, it just suggests it using the power of the additive white noise. So that's the power and the variance are the same thing in engineering, because the mean of the signal is 0. If the mean wasn't 0, the average, then it would be slightly different. But we always deal with 0 mean signals, so the power is the same as the variance, so it's going to be 0.5. And so it's generating this. I'm assuming that's going to be uncorrelated with the original one, but it seems to work anyway. And then it adds the signal and the noise here. Then it applies a Wiener filter. I mean, it doesn't, because there's no information of how it does that. My size, I'm not even sure. I assume that's something to do with matrices or something that it's using, but I don't really know. And then this is just all the plotting stuff. So I copied that directly, but to make things a little different from previous videos, I'm using this other thing called for compiling Python, which is called PyCharm. And there's a PyCharm community. It's supposed to be one of the good ones. Oh, of course, it's got debugging, whereas the other one I use, the Thorny editor, doesn't have debugging. Not that I really need debugging for these things that much, but it nevertheless, and it's a little bit more tricky to use in that it throws up more. It's not so forgiving, is what I really need to say. But because I hadn't put in any of these libraries, then it comes up with errors. So for example, here it says I've put some of them in, but this one I didn't, so I can show you how to do it. So it comes up with unresolved reference SciPy, and if I just click on that, I can do show quick fixes. That's quite interesting. And then it says install package SciPy. I mean, I could have done that anyway, of course. It's saying it doesn't find Wiener and low pass filter, but those are part of SciPy, so that's probably the reason. So it should work after I've got rid of that. Here it's complaining about a blank line at the end of the file, which let's see what it. So it's not. There's no quick fix to that. It should be okay. Let's try it now. Oh, and there we go. That's as simple as that. So the blue here is the random signal, and the orange, I think it is the filtered signal. Make it a bit bigger, and that is absolutely fantastic. So I mean, I didn't need to know an awful lot. I need a little bit about Wiener filters, but off it went. It did it. Of course, it doesn't tell me the method it used. So what I did was I went back to chatGPT, and I asked it. My question is, how does SciPy signal.wiener, the library, calculate the Wiener filter? I didn't actually use those words, but it sort of paraphrases it, and it gives me a huge amount of kind of stuff I don't want. And then eventually it tells me here it uses the frequency domain. It does it in the frequency domain using the fast Fourier transform, and that's one of the oldest methods really that's used. It's not something I use a lot myself. Some of my research students used it for speech enhancement and so on, but it's a straightforward way. That way you can use the actual real data rather than the transfer function model. But I mean, you can use the transfer function model and do spectral factorization and a whole lot of stuff, which I thought it might do that, but it doesn't. It does it presumably from the data itself, but it you have to sort of follow that up with a reference there, and gives an example here as well. So another example of how you can use ChatGPT as a teacher, how to teach yourself things, whether it be the software or not. A little bit about this thing called PyCharm, which is supposed to be a very good environment for Python. It is rather nice. It's a bit fussy, as I say. It puts it in this sort of virtual environment, and it's a bit of a mess to actually put together on Windows anyway, and I guess in Linux it's probably not much better either. But once it's set up, it's pretty good actually. You can see how it corrects errors there, and it gives hints as to how to fix things, which is pretty clever. I mean, as an old programmer, we always used to say in the past, if the computer knows, let's say, a syntax error, and it knows it's a syntax error, why can't it correct it itself? Of course, that's not a good example, but here it kind of suggests solutions, which is rather nice. Anyway, so that's the SciPy thing. So thank you for watching, and I'll see you next time.